Greetings. I myself am Dr. Shivabalan KR and I am presenting my single page poster in accordance with the 42nd Annual International Conference of the IEEE Engineering in Medicine and Biology Society in conjunction with the 43rd Annual Conference of the Canadian Medical and Biological Engineering Society. My poster is on characterizing working memory load using non-linear analysis of EEG signals. I myself am Dr. Shivabalan KR. The other doctors who are involved in the study, the other co-authors respectively are Swati Kiran, Aravind Ramachandran, Suryabala S, Kevin Arulraj, and Abhishek Anand. Abstract: in this paper, we have analyzed the EEG signals obtained from an open source database, PhysioNet. We have adopted nonlinear dynamic analysis to characterize and differentiate the subjects who can perform a mental task, good or bad. We have actually developed a classification system using a support vector machine to differentiate rest and task states. The relevance is the same could be extrapolated to subjects with dementia or minimal cognitive impairment, and we could detect such degenerative processes at an earlier stage. It also provides an insight on the chaotic nature of the brainwave dynamics in humans and could help in understanding neurodegenerative diseases. It can also help in ensuring productivity in task completion. Introduction. A reliable and cost-effective method of assessing working memory is crucial in decision making. EEG is an easier tool to assess the brain activity, and utilizing nonlinear analysis of the same can yield many parameters which help us to understand the chaotic nature and organization of the brain activity. In this paper, we have actually tried to understand the same chaotic nature of brain waves in the face of serial cognitive overload in normal subjects and discrimination of the good and bad performance. All the EEG recordings were obtained from the physionet.org, and each EEG recording include a separate artifact-free EEG segments of around 180 seconds for resting state and 60 seconds for the task state. Independent component analysis method was used to eliminate the artifacts, and based on the number of arithmetic operations per minute, the sample was divided into two groups. The proposed task was a difficult task for one group of participants, where the second group managed the task without difficulty. EEG signals were recorded for in both groups during rest and task state, and subgroups were finally obtained using wavelet power transform, and the following features were extracted using MATLAB R2018B, which were power spectral density, sample entropy, fuzzy entropy, and fractal dimension. We found that the good group has a lower entropy and fractal dimensions of theta and beta Ben in frontal lobe than the bad group, while the good group has a higher entropy and fractal dimension of theta and beta in the occipital lobe and the temporal lobe. We found finally that power spectral density and fractal dimensions are good discriminators to characterize memory load in an arithmetic task. When the difficulty level of the task was increased, the frontal and the occipital lobe regions were affected more and deeply and widely. The extracted features log, power spectral density of alpha and gamma were fed into SVM, KNN, and linear discriminant analysis for classification of rest and task state. The tenfold cross validation was used to divide the samples into 10 parts, and one of the 10 parts were used as a testing state, and the remaining 9 parts were used as a training state. The mean value of the tenfold cross validation was used as the accuracy of this model, and we found that SVM has the highest accuracy of 85.31%, while the accuracy of KNN and LDA was there 83 and 77% respectively. Thank you so much.